So last time we were talking about the direct comparison test. Oh, by the way, I was gonna give us a handout today to work on, but I got into work and there's no power in Scott Hall. So I was in my office with my cell phone light grabbing my stuff, and hopefully it'll be going by 10 o'clock because I have a class in there at 10 o'clock. So we were talking about the direct comparison test, and the concept here is that if you have two series, A sub n and B sub n, where A sub n is always less than B sub n for all values of n, and either one of these is true, so if B sub n converges, because A sub n is always less than B sub n, then A sub n has to converge anyway, because it's always smaller. Likewise, if A sub n diverges, which is the smaller one of the two, then B sub n also has to diverge because it's always bigger. So a lot of times we're able to come up with a series test that works for one of the two, but not for both. It works for one of them if you simplify it. So our example here was A sub n has n squared plus 1 in the denominator, which we can't use any of the tests that we have so far to evaluate it. But if we remove the 1, this term, this nth term in the series of B sub n is always greater because you always add 1 to the denominator, which makes the denominator bigger. So in this case, A sub n was always less than B sub n, and what we did is we were able to use the p-test to determine that this converges, so therefore this converges. Okay, so that's the basic idea. So we got one more example before we go to the next test, which is, so here's the example. So it's the natural log of n over n plus 1. So what we would do is, usually when you're adding 1 or adding something to the denominator, it always makes the denominator bigger. So that's always kind of a key, which test should I use? Well, so what we'll say is A sub n is the original term in the sequence, and B sub n will just drop the 1, so you'll have the natural log of n divided by n. And in this case, A sub n is positive, pardon me, B sub n is, yep, that's the right way. Gotta make the right order. So A sub n is always less than B sub n. I don't really need to prove that, just because anytime you add 1 to the denominator, it gets bigger, and therefore a bigger denominator means it's a smaller number. So what we're going to do is we're going to look at the convergence and divergence of the series that involves B sub n. So we look at the summation from n equals 2 to infinity of the natural log of n over n. I think we did that earlier. If you use the integral test, I'm not going to work through it, but because I think we've already done it before. But if we did the integral from the natural log of x over x dx, what we would find is that converges. And why is that? That's because when we look at integrals like this, if the, well, actually, we might not know. I think you have to use L'Hopital's rule or something. We did do that one, didn't we? Yeah. Well, you have to use L'Hopital after you evaluate it. Let's just, I thought we did this, but I don't remember exactly. So let me not skip it. I think I'm pretty sure it does converge. It's not L'Hopital's, L'Hopital's rule would say that the limit of this as x goes to infinity is 0. But that's not, we're integrating it, so you can't necessarily do that. So what we would do is find the limit as b goes to infinity of the integral from 2 to b of the natural log of x divided by x dx. And this would be a integration by parts problem. So we would so let's just do the indefinite integral. And so we're just going to do that on the side and then plug it back in when we're done. So you'd let u equal the natural log of x, and you'd let du equal 1 over x. Sure seems like we've done that before. Let me open up the last. I don't want to do it again if we've already done it. So let me just open up the previous section notes for the integral test. See if we did it, so we don't have to go through the whole thing.
We did over n squared.
N squared. Oh, okay, is that what we did? Yeah. So it is slightly different. Okay. Well, we'll go ahead and do it then. So du would be equal to 1 over x dx, and this would be dv, sorry. So the integral of dv, this is x to the minus 1 power, which is, yeah, you don't even have to use u substitution. You just use u substitution, you're right. Yeah, you don't have to use integration by parts. You would just let u equal the natural log of x, and du would be equal to 1 over x dx. Yeah, I was realizing that when the integral ended up being the natural log, and that doesn't make sense. Okay, so what you can do is then rewrite this as the integral of u times du, and the integral of u du is u squared over 2 plus c. So you plug that back in, and u is the natural log of x, so you have the natural log of x quantity squared over 2. Okay, so we take the limit as b goes to infinity of the natural log of x quantity squared divided by 2 evaluated between 2 and b. So actually this is going to diverge. It's lucky we didn't do that, so that's not true. And it was because the previous one is over x squared. This one doesn't. Okay, so then let me come down here. So what you have then is a limit as b goes to infinity of the natural log of b quantity squared divided by 2 minus the natural log of 2 quantity squared over 2. And you can see as b goes to infinity, this term is going to go to infinity. So we get infinity. So it actually diverges. So we come back over here. Now that we know that the b sub n, the series involving b sub n diverges, because the integral diverges, the series diverges. Because b sub n diverges, therefore a sub n also diverges. Or wait, is that true? Am I using the right one here? Does it? Yeah, that's right. Yeah. Yeah. So let's write that out because it's kind of confusing once you do it. So we can say since a sub n is always less than b sub n, and it's always greater than 0, and the series, the summation of b sub n from n equals 2 to infinity, diverges according to the integral test, the series, the summation of a sub n as n goes from 2 to infinity, which is the same as the original function, which we had the natural log of n over n plus 1. Diverges. So it's kind of a multi-step process. The original series, we didn't have a test that works for it. So we figure out a series b sub n, which is simpler which can be evaluated using another test besides the direct comparison test. We look at that and we say, it looks like something I could integrate. So we do the integral instead of the series from 2 to infinity. So we did that separately. We found out that this integral diverges. And because this diverges, and this is always greater than, actually that's the wrong way, isn't it? Yeah. Yeah, that's what I was thinking about. I was getting confused. So let's see why that doesn't. The problem is it works for if it converges. So the question is, what the heck do I do now? So, because this is the one we're talking about, and in this case, a sub n is yeah. Let me think about that. Hold on. My mind's going in one direction. Well, we haven't talked about that yet. So but you can use the limit comparison test. So is there any other way we can do this using the direct comparison test? Maybe I had to use the limit comparison test. Maybe that's why I put it in there. Yeah, so just because this one diverges doesn't mean this one diverges. Well, if it's in the right order. Well, it says that. It says if it diverges. If this diverges, then that diverges. Okay, so this would be the alternate function. I guess I could subtract 1. No, I can't do that. I just dropped the 1. Yeah, you might have to use the limit comparison test. You're right. Did I bring my book? Yeah, you can see that the other problems, what happened was that this converged, therefore this converged. But in this case, B sub n didn't converge, so I can't use the same reasoning. So just because this diverges, this is a little smaller, so it may not diverge. It does actually still diverge, but you can't use the direct comparison test. Okay. So let's talk about the limit comparison test, and then we'll see how this works. Okay, so the limit comparison test, in the cases like we just had, where the alternate function doesn't fit the requirements of the direct comparison test, you can use the limit comparison test. So the requirements are that a sub n is greater than 0 and b sub n is greater than 0. And if the limit as n goes to infinity of the ratio of a sub n over b sub n equals some number, could be 0 or it just has to be a finite positive number, then there's really no restrictions. So if one of these series converges, the other series converges as long as that limit goes to some value L. The direct comparison test has that little tricky thing that we just experienced and easily fall for because I fell for it ultimately. So you have to be a little careful. So let's do the problem we just did, showing how you would use the limit comparison test and find out that actually it does diverge, but not because of the direct comparison test. So let me actually it's probably easier too, right? No, it's not as it's not as easy. Yeah. So let me just add on to this because we've already got everything we need to solve the problem. So all you have to do is take the limit as n goes to infinity of a sub n over b sub n. So a sub n was the natural log of x divided by n plus 1, and b sub n was the natural log of x over n. And you can see that these can't, let me make sure I put n's in there. They should all be n's. Let me rewrite that. So you've got the natural log of n over n plus 1 divided by the natural log of n over n. And the natural logs cancel out, and so this simplifies down to the limit as n goes to infinity of n over n plus 1. And the answer is 1, because it's a rational function and the leading coefficients of the highest order term are 1. So, or you can also think that the 1 added to the denominator becomes insignificant when n becomes very large, and so it's essentially n divided by n. So that fact there says it satisfies the requirements for the limit comparison test. So now all we have to do is look at the convergence of b sub n, which we already done. So we can go back now and say, since the limit as n goes to infinity of a sub n over b sub n equals L, which in this case is 1, we can apply the limit comparison test, and therefore, since b sub n diverges, a sub n also diverges. Okay. There's another kind of problem which I have on the next screen. What if you subtract 1? What if you have the denominator n squared minus 1, or n minus 1, or the natural log of n over, well, if you had the natural log of n over n minus 1, that one you could actually solve using the direct comparison test. But if it's minus 1 in the denominator, you can't use the direct comparison test, but you can use the limit comparison test. So let's just look at that problem. So we looked at the case of 1 over n squared plus 1. When you have 1 plus 1 in the denominator and you let b sub n be 1 over n squared, b sub n is always greater than a sub n. But if you subtract 1, it's the opposite way around, because the denominator is smaller and therefore the fraction is bigger, and so you can't use that to prove it converges. So what we do in this case is we let a sub n be the original term of the infinite series. We again simplify it down by removing the negative 1. And if we take the limit as n goes to infinity of a sub n over b sub n, you get 1 over n squared minus 1 over n squared, which, if you take the reciprocal of the denominator and multiply it out, you get n squared over n squared minus 1, which is equal to 1 again, for the same reason that the last problem was that case, because the leading coefficient of the highest order terms are 1. So it satisfies, just like in the previous example, it satisfies the requirements for the limit comparison test. So now all we have to do is look at the convergence of the second series. So if we look at the summation from n equals 1 to infinity of 1 over n squared, not our original series, what we would do is we would say the summation of b sub n is a p-series, and p-series converge if p is greater than 1. Therefore, this series converges. Therefore, lots of therefores. Starting to sound like a lawyer. Therefore, the original series summation from n equals 1 to infinity of 1 over n squared minus 1 also converges according to the limit comparison test. Okay. So you don't always use the same test to prove that the alternate series converges, whatever's appropriate. So let's look at another one. So it's pretty close to the one I just did. Trying to think about why could I use the direct comparison test to do that? Probably, but they ask us to use the limit comparison test, so we'll use the limit comparison test. So that first one we must have been able. I'll have to go back and look at that one. Why? It seems like it was in the section that said use the direct comparison test, so I'm not sure what I'm missing. It looks like the limit comparison test is more flexible. So what you would do again is you would say a sub n is the nth term of the original sequence. You'd let b sub n equal n over n squared, which is the same as 1 over n. So you would look at the convergence of this. Well, first you have to look at the limit. You have to evaluate the limit as n goes to infinity of a sub n over b sub n to see whether the limit comparison test applies. So you'd have the limit as n goes to infinity of n over n plus 1, n squared plus 1 divided by n over n squared. And again, you could take the reciprocal of the denominator here. So you'd have n over n squared plus 1 times n squared over n. And you can see that goes to 1, hopefully. I mean, ultimately, you'll have n cubed. You have n cubed over n cubed plus n. So when you use the leading ratio of leading coefficients, you get 1. So because that equals 1, then the limit comparison test can be used. And then all we have to do is look at the convergence of the second series. So the second series is 1 over n summation from n equals 1 to infinity. And this diverges because it is a p-series. So it diverges because of p-series since p is equal to 1. And p-series converge only when p is greater than 1. So if p is equal to or less than 1, then the p-series diverges. So it equals 1, it diverges, and therefore you can kind of say the same verbiage about convergence. I'm not going to write it all out, but hopefully you see again. First you check to see whether the limit of these two series goes to 1 or to any number really. Then you look at the simplified series that you're comparing it with, You look at the convergence of that, figure out what kind of series it is, so you can use the appropriate test, apply the test. If this diverges, then the other one diverges as long as this ratio is equal to some fixed value. And the same deal here. You'd let a sub n equal 3 over the square root of n squared minus 4, and b sub n would be 3 divided by n. And how did I get that? Well, because if I drop the negative 4, I'll have the square root of n squared, which is n. So this would be if I take the limit of a sub n over b sub n as n goes to infinity, it's equal 1 again, because the 3's will cancel out. You'd have to use section 3.5. There were those special cases of where you have n over the square root of n squared plus something or other. So you can show that limit equals 1, and because it equals 1, it means that if this diverges, then that diverges, and we already know that diverges because it's a p-series. So again, I'm not going to write the whole thing out. Okay, so now I'm going to assign the homework for that section. Actually not. Well, I am going to give you a break here. Give you 10. Write down the numbers. What we're going to do next is we're going to look at some different series and see if we can figure out which is the appropriate test to run of the ones that we have now. So we have the nth term test, which really tells you whether something diverges. We have if it's telescoping series, we know how to deal with that. Geometric series, p-series, the integral test, the direct comparison test, the ratio test. There's only 2 more tests that we have to present, which we'll do in the next section. So we have enough tests now that we can try figuring out which is the appropriate test. And we'll do that next time. Once the power's back on, I can make some copies. So tomorrow we will have a handout, and there are probably 20 some different problems, and we're going to look at them and figure out which tests we're going to use for each one of those. Except we don't know the ratio or the root test yet, but let's look at this. Okay, so these are the tests: the nth term test, the geometric series, the p-series, telescoping series, integral test, direct comparison test, limit comparison test. Okay, so I didn't miss any. So here's the first problem: summation from n equals 1 to infinity of the square root of n over n. What is the nth term test tell us? So if we take the limit of the square root of n over n as n goes to infinity, does that equal 0? The answer is yes. Okay, because if you simplify it down, it's 1 over the square root of n. So as n goes to infinity, you're going to have 1 over infinity. So it does go to 0, which means we can't just rule it out. We can't just say it diverges immediately. And then you look and see if it fits any of these. Is it a p-series, a geometric series, a telescoping series? And you may ask the question, can I simplify it? And the answer is yes. Okay. So if I simplified it, can I do math on the terms in the series? Yeah, you can. So you end up with 1 over n to the half power. Okay, anybody know what it looks like now? P series, yep. And P is equal to a half. And if you pull out your sheet, that I handed out the other day, because that's what we're going to be using. You don't have to. So look at the convergence criteria for the p-test. So Maya, what does it say for? Yeah, so P is P greater than 1? No, so it diverges, right? So what we can say is first it's a P series. That's the first test. P series, P is equal to 1/2, which is less than 1. Um, so the series is a P series with P equal to 1/2, which is less than 1. Therefore, the series diverges. Okay, let's move the next one up so we can still look at the list of options. Okay. So does that look kind of familiar? If I took the 2 away, so let's just see if we can identify the series that so is that a P series? Kelly, is that a P series?
Yes.
Okay. So here's what a P series looks like. Does the base of the series change? What's the base of that exponent? 3. So with a P series the base changes. So it's not a P series. It's not a P series. How about a geometric series? Does it look like a geometric series? Sorta, right? So what if I rewrite this as so 1 to the n power is equal to 1 squared is 1 cubed is 1, right? So this is a valid thing to do. Normally you go the other direction. You'd say 1 to any power is 1. What I've done here is I've said 1 is 1 to any power. As a consequence, this is really 1/3 to the n power. Okay, now does that look like one of the series that's not a P series that I have up there? The answer is yes, right? It's a geometric series with R being 1/3. Okay, so initially it doesn't look like the original simplification doesn't look like a geometric series, but it is a geometric series, and even if you had a whole number in the numerator, you would pull that out. Say if it was 2 divided by 3 to the n, it'd be 2 times 1 to the n over 3 to the n. So anyway, that's a geometric series. So we can look at the convergence of that simplified thing. Does that geometric series converge? So look in your paper again under geometric series. So Kelly, I'm going to ask you because you. So what are the convergence criteria, and what values of R does it converge for?
R is less than 1.
Yep. So is R less than 1?
Yes.
Yes. Okay. So since R is less than 1, that converges. So we can either use the direct comparison test or the limit comparison test, and that's because I'm adding 2 to the denominator, and because I know B sub n converges. I know that if that converges, then the original one can converge. So I can use either the direct comparison test or the limit comparison test to answer the question. So let's just look at how you would do each one of those. So the direct comparison test a sub n is 1 over 3 to the n plus 2, and b sub n is 1 over 3 to the n. And we can use the direct comparison test because a sub n is always less than b sub n, because I'm always adding 1 to the denominator. So this is true. And since b sub n converges and a sub n is always less than b sub n, then a sub n converges. Okay. Whereas if you're using the limit comparison test, you take the limit of a sub n over b sub n as n goes to infinity. So that would be equal to the limit as n goes to infinity of 1 over 3 to the n plus 2 divided by 1 over 3 to the n. That one's not quite so obvious that it does equal 1. I'm trying to think about how you would do that besides just waving your hands and saying it's true. So if you simplify this, you get 3 to the n over 3 to the n plus 2. It's not really one of those cases where the exponent is n, not the base. Before, when we've done that, we've been able to simplify it using the leading coefficient test. So how would we do that? I guess one way is if you plug infinity in there, you've got an indeterminate result. But every time you take the derivative, you're not simplifying it any. So maybe that's why this would be better. It's easy. It's not as obvious. I mean, you can kind of reason that 3 to a large power, the 2 becomes insignificant, and the ratio will become 1 at some point. So it's kind of obvious that it is 1. But I'm trying to think of Evan, you know about it. Yeah, L'Hopital's rule. But I think if you took L'Hopital's rule, you'd still be infinity over infinity, because you'd end up with n times 3 to the n minus 1. Pardon me? Oh, you're canceling them out. Yeah, that's true. Actually, I thought about that, and then somehow I convinced myself it wasn't true. So, yeah, so by taking the derivative, you get rid of the 2, so you're just left with this, and everything cancels out. So even though it's still infinity over infinity, because at this point you can cancel stuff out. So good point. I hadn't thought about that before. Yeah. Yeah. Yeah, I mean, it just allows you to get rid of any, if you had 3 to the n plus n's 2n plus 1, when you take the derivative, ultimately, if you take the derivative enough times, all the polynomial stuff falls out, and you're just left with those exponential terms, which cancel out and become 1. So anyway, it does satisfy it. And so since this is satisfied and this converges because it's a geometric series with r less than 1, then we know it works. So those. Okay, let's look at the next one. So it's it's not a. Could it be a p series? I guess if the first term could be a p series, couldn't it be? Here's p, 1 over n. So the base is n. So it's different than the previous one. So I could see that the highest order term is a p series. Now I'm subtracting numbers from there, so I probably can't use the direct comparison test. If I was adding 2n plus 15, I could probably use the direct comparison test. I could use L'Hopital's rule, or just looking at, actually we know that. Yeah, we could use the reading. Yeah, so I think because we're subtracting numbers, you couldn't really use the direct comparison test. So what we would do is we would say a sub n is equal to 1 over 3n squared minus 2n minus 15. B sub n would just be 1 over 3n squared. And because the limit as n goes to infinity of 1 over 3n squared minus 2n minus 15 divided by 1 over 3n squared equals 1 again. Why? Because if we take the reciprocal of this, this will come to the numerator. We'll have like a polynomial. We have the same highest order term, so the ratio of the leading coefficients is 1. So because that's satisfied, we can use the limit comparison test. And then we can look at this and see whether it converges or diverges. And what's the p-series? So Lexi, what does it say? For p-series, what does p have to be to converge? Greater than 1. So is p greater than 1? Yes. Okay. So p is greater than 1. So again, I'm going to write out the whole thing, the explanation here. Since, well, let's say if we choose b sub n equal to 1 over 3n squared, and the limit as n goes to infinity of a sub n over b sub n equals 1, the limit comparison test is applicable. Okay. Then, since b sub n, which is equal to 1 over 3n squared, is a p-series, and p-series converge if p is greater than 1. The series, the summation of b sub n from n equals 1 to infinity converges. Therefore, since b sub n converges, a sub n also converges according to the limit comparison test. Exclamation mark. Okay. So the first thing we did was we said, it was a fairly complicated function, so we probably said, oh, we can't use any of those simple tests. But if I drop all the highest order terms, or all the lower order terms, I'll end up with something that I recognize as being one of the series that I can easily look at the convergence of, which was this one. And because this is a p-series and p-series converge with p greater than 1, b sub n converges, and because the limit of the two expressions, the nth term of each series equals 1, we can apply the criteria for the limit comparison test. So that one works. That's a telescoping series. We'll skip that one for right now. So what do you think about that one? That's fairly complicated. Is there a function that we can replace with that? If we drop the 1, what would it simplify down to? So we drop the 1, it's going to become n over n to the 4th. So the here a sub n is n over n squared plus 1 squared. What we do is we choose b sub n to be 1 over n cubed. That's because if I take the original expression and drop the 1, I'll get n over n to the 4th, which simplifies down to 1 over n cubed. And that's a p-series again. So because this is, I'm not going to write it all out, we just did one like it. Because this is a p-series with p greater than 1, this converges. If you take the limit of a sub n over v sub n, you're going to get 1 again. You might have to use L'Hopital's rule to prove that the limit is equal to 1, but it is. And so because this converges and the limit of the ratio of these two goes to 1 by the limit comparison test, that one converges as well. Let's look at another one. I already did that. Okay. Okay, so that's it. We're not doing the we'll come back and do that when we do our handout. So I'm just going to introduce you to the last two tests now. Oh, actually, there's two more sections. Sorry, forgot that. As we've seen early on when I was demonstrating the sine and the cosine, those are alternating series where the terms alternate between positive and negative. And so there's a special rule for alternating series, which is a little bit more forgiving than if it's not an alternating series. And that's because you're adding and subtracting numbers together. So you can have, if you add 1 over n, the series 1 over n diverges. But if you have it alternating between negative and positive, that one actually converges. So it's, as I said, it's more forgiving as far as convergence. So here's the test. So it says let a sub n be greater than 0. The alternating series is defined as the summation from n equals 1 to infinity of negative 1 to the n times a sub n. So a sub n is always positive. You get the variation in sign from negative 1 to the n, and it can be either e to the n or to the n plus 1. That just varies it whether it's the first term and the first term's positive and the second term's negative, or the first term's negative and the second term's positive. So they both converge. I mean, they both alternate. And the only convergence criteria for this is that the limit of the positive part, the non-alternating part of the series, goes to 0. So that's kind of like the nth term test, except the nth term test says if this doesn't equal 0, it's going to diverge. In this case, if it goes to 0, plus if the nth term, n plus first term, is always smaller than the nth term. Obviously, if this goes to 0, this has to, ultimately, the last term has to be smaller than previous terms. It would never go to 0. Here it's just saying that it has to be continuously decreasing. So if I plotted a sub n as a function of n, it would go to 0, and it would go monotonically down to 0. It wouldn't go like doot 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 doot. So they're always getting smaller as they approach 0. And if those two are satisfied, then the alternating series converges. So some things that wouldn't have converged that were non-alternating series do converge as alternating series. So let's the one that we've seen the most of, and it may be on what's on the next page. But if I did this series, the summation from n equals 1 to infinity of negative 1 to the n times 1 over n. And compare that with what we've already seen before. If we have the series, the summation from n equals 1 to infinity of just 1 over n, that diverges. And that diverges because it's a p-series with a p-series with a p of 1. And so according to the rules of the p-series, that the second series diverges. But if you look at the convergence criteria for an alternating series, you'll see that if we look at the alternating series, all we have to have for this to go to be convergent is we have to look at the limit of 1 over n as n goes to infinity, and that's 0, so that's check. And also, if you take 1 over n plus 1, is that always less than 1 over n? So what I've done is I've said a sub n plus 1 would be 1 over n plus 1, and a sub n would be 1 over n. And the question, is that always true? And the answer is yes, but how would I prove that? Well, if I cross multiply, I'll get n times 1, and then I'll get n plus 1, and if you subtract n from both sides, you get that, which is always true. So because this came from the original inequality, if this is always true, then that's always true. Therefore, a sub n plus 1 is always less than a sub n, so that's satisfied. And with those things satisfied, so what we did here was a sub n plus 1. Is that always? Are there any conditions under where that's not true? And the answer is no. So what we can say here is, since the original series is an alternating series, and the limit as n goes to infinity of 1 over n equals 0, and 1 over n plus 1 is always less than 1 over n, the series converges. If you look at your table, what does it say in the table? It probably says something like that. If you look down at alternating series. So it defines what it is, and it says that the two requirements are that a sub n plus 1 has to be always greater than a sub n, has to be positive, and the limit as a sub n of a sub n as n goes to infinity equals 0. So it satisfies the convergence criteria, and hence it converges. So really any p-series, if you think about, it doesn't matter what the exponent is. I could have n to the half power, which would normally, 1 over n to the half power would diverge, but the alternating series of 1 over n to the half power would converge. Okay, so we'll finish there for today.